So, yeah, while we are always doing stuff specifically for mortgages and finance, the goal all along has been general data manipulation and querying of relational databases. So I'm going to show you our latest and greatest, which we've been working on for a while. And I'm going to start with a simple query. FlipDB has a relational database backend, all built in Dyalog APL. It's an inverted or column store database, which is very trendy now. Of course, in APL, we've been doing that for 30, 40, 50 years, but now they call it a column store. And one of the things about a column store is it doesn't really make much difference unless you have a column-oriented query language, which, as you all know, APL is array-oriented, and we're very used to taking a vector and summing it up and reversing it and summing it, scanning it backwards, and doing all those sorts of things. And the goal here is to make simple things simple. So if you're doing a standard query, select some columns, select some rows. That's really easy. Grouping, all the things you could do in SQL. And then if you can conceive of an APL solution, you should be able to do that too, very easily. Accessing any column, searching up one column, linking tables, anything like that. So I'm just going to start with a simple query, and we'll kind of go through some examples and see where it leads. So the first few examples are using a little baseball statistics database. And this isn't going to work. Hold on here. So we're going to launch a little query here. And we're going to see this one here, current teams. So in FlipDB, a query is, it kind of can be thought of as a highly structured dynamic function, a set of names and expressions. And they're in sets of names and expressions. And there are different sets that perform different tasks, and they're ordered. So you can see them all across the top of this little ribbon. You start by specifying a source, and in this case, I'm specifying a database and a starting table. The next thing that you might want to do is compute some columns, and in this case, I don't think I have any. There are no computed columns. But if we wanted to start and just compute some new values in here, we could do that. And again, it's just a set of names and expressions. Then you might want to apply a where clause. And here I have a very simple where clause. I'm just looking where the field active is equal to yes. We can have multiple where clauses, and we'll see some examples of that as well. And we can also do a where not, which is quite useful, and we'll see some examples of that. There are none here. And then we can specify what columns we want to see. And here I just picked 2 columns, and in the process I rename them in my resulting name and my expression, but my expression is just trivial. It's just the name of the column. And I believe that's it for this query. We can look at the query definition here, and we can see it kind of laid out all of the different components in order. So we can see exactly where we're selecting our data. Do we have any where clauses, any where not, or any quotas, any grouping? And finally, we're just selecting it. Simplest query, and there are the results. So let's jump to a more interesting example. Let's say number 2 here, the team summary. Let's take a look at the overall query definition here. So here I have 2 where clauses. Notice that I'm also doing a little dot syntax there in the second one where I'm asking for the name to be equal to the franchise ID dot franchise name. I set up this database with a foreign key, and that's a foreign key at the table pointing to another table to get another column. Then we're doing a grouping by team, and then we're specifying some measures. And Note the measures, again, each one of these sections are just names and expressions. And if you look at the measures, we're counting to get the number of seasons for each team. We are looking at the number of World Series appearances, World Series championships, and then we are summing them up. And then a little bit more down there, I'm computing a winning percentage. And notice that I'm using values in that winning percentage that are specified in the line above. So just like a dynamic function, every line you can refer to the value that you defined above. So I use in winning percentage, I'm looking at games won, games played, and they're defined right up above there. So it's really just a thin cover for a defund if you think about it. Now we can trace this and kind of see a little bit more how it works. So if we take the tracer, we can trace through step by step each part of this. There are no computed columns. We can step through there. We do have, let's make this a little bigger here. Okay. With the where statements, they're really names and expressions as well, but the names, we don't tend to name them, so the system names them automatically for you. But you can step through them, and in each step, you can see how many were selected, how many are true or false, and it's a little bit of a waterfall, right? After you specify one, then you have less to start with. So here we're starting with 2,800 records, and we're selecting 2,600 by that first expression. And then in the second expression, we're starting with the 2,600, and we're tossing out 640 and getting a few less. So you can step through each one of these. And there are no where not statements. We'll skip that. And then we group by the team name. And it just shows you the statistics there as you're grouping. And now we're going to go through our select expressions. This would be a select expression in SQL, but here I tend to call it a measures property. When you have a grouped query, you're generally going to aggregate things, but you don't have to. So the first time I'm just doing a count. So here the thing to note is because we've grouped, auto key is just an automatic system-provided automatic key for every table. So because we have a grouped query, the value of auto key in that expression, where we're doing the count of the auto key, is a nested vector, essentially. It's a partitioned column. And you can see that there when we display it on the right in the bottom panel. Then I want to count up the sum where the league wins are yes. That's a league win for each team. And the same thing here. The league win is a nested partition column based on our grouping criteria, and we're summing it up where it equals yes, and so on. So we go through there. We can do the same thing for, here we're just summing up the number of games played. Those are columns that are in the database. Sum of W, sum of L. And here we're using those things that we just calculated to do a further calculation. And we get our winning percentage. And then we just trace through pretty much the whole query there. I think that's the entire query. Oops, I lost my query there. I'll go to the next one. Okay, so one more. Actually, let's bring that query back up there. Here it is. Okay. And there's that query again, and we can see our final results here laid out where we're grouping by each team. And we've actually sorted this by the number of wins, World Series wins, so we can see here. I'll get that a little bigger. You can see Yankees won 27 times, and they're pretty much in first place. Okay, so I think we have one more of these kind of simple queries here before we get to the interesting stuff. Just get rid of that. Whoop. So here we have a batting average. This looks at a table of every player, every season, for the current seasons actually, or the most recent season, what their batting average is. And let's take a look at this query definition here. It highlights a few. Here we have a computed column as well. We've got a where clause. We have a group by. And we have, since it's a group query, we have measures where we're computing batting average, looking at the sum of the hits, sum of the walks, and a couple of different things. Again, we are looking at expressions that refer to the expressions ahead of them in the query. All right, so let's do that. Also note here, we're looking at a couple of foreign keys as well. And that's, this one actually, in this expression here, when you have a relational database and you set up foreign keys ahead of time, it's easy to link things back and forth. But often you do not have the luxury of setting up foreign keys and setting up relationships. They may not actually be foreign keys. You may have many-to-many relationships. You may have all sorts of things that you're just dealt with. And one of the things that we have to deal with is the data as given. You may not have time to clean it up and normalize it and do all that sort of stuff. So that first expression under computed columns, we're looking at another table, the teams table, and we are looking up based on two different columns, team ID and year ID, and getting the name from that other table. There's an implicit argument there on the other side of the semicolon, which specifies the names of the columns in the other table, but they're the same, so we can elite it. So that's doing a two-column lookup based on whatever happens to be in there. We're not necessarily, if they turn out to be they're unique, you'll get a simple column back, and if they turned out to be many-to-many, you'll get a nested column back with all of the information in it. So let's just trace through that real quickly. Go back to the tools, do the tracer. And that's what's going on there. So we're computing that ahead of time. So this is using the computed column property to just specify that we'd like this new column. Notice that we're not having to deal with joins of entire tables. We can deal with the whole database on a column-by-column basis by just pointing to which columns we need when we need them. Here I'm only interested in current years because this table has stuff going back to 1910 or something in it. So I just want the year ID for the most recent year. I think 2017. Yeah, it goes back to 1871 in this database. I don't have any where not statements. And then we step through our expression. We group by the player. I want to grab the name. I'm summing up each player's at-bats, summing up the hits, summing up the walks, taking a batting average. I'm not sure that's exactly how you do the batting average, but something like that. And again, notice that we are using values previously computed. And then finally, we want to display the team. And a player may be on 3 or 4 different teams during a season if they're traded. And this will show, so the team name actually could be multiple teams. I want the unique values in there, and then I want to make a toCSV as a aggregate function that takes a text, any column, and if there are multiple values per row, it will put it into a single text string, which is useful. And in fact, you can see that there's some players who played on multiple teams. And so it takes a structured thing like this, where I have 2 items, and it creates a little comma delimited string. So this player played on the Cardinals and the Braves in one season. And we use both of those sets of stats to compute his batting average for that season. All right, so those are basic queries, things that if you use SQL, probably not that hard to do in SQL. There's a whole other class of queries that come up in our line of work, and a lot of lines of work, and you see systems specifically built to do these kinds of things. And whether you're in, especially now with all these new products like Tableau, they will have these completely separate from a structured query language or a generic query language. They'll have these tools for cleaning up your data to get it ready so that you can then do some analysis with it. And here we can use all of the same exact tools to do that. So you don't have to have a different set of tools. And furthermore, they're essentially APL tools that you all know and love and you can apply. So while an average user of this may not have the APL skills, they can do everything easily and they can ask, how do I do this? And then you can just give them a little pseudo APL expression that does it. And there's no need to resort to ad hoc programming or scripting or anything else to get a very complex problem solved. So let's look at some of them. Let me close that. And I have a next one here. Let's see. Okay. So one of these, there's a set of these challenges from a company called Alteryx, which is one of these companies that provides a data manipulation cleanup tool. And they've conveniently put out hundreds of interesting challenges that you can test your chops against. So the first one we're going to look at is this one here, challenge 121. And this challenge, you're looking at a slightly different screen here. You're looking at a screen that is essentially a dashboard, which is a collection of queries. So I'm looking at the first query, which is just displaying the given input that they're giving you for this challenge. And it's a single text field with some data in it about the 2016 World Cup. And it lists all of the stadiums and all of the games that are playing in each stadium. Okay? So you see there at the is that big enough there? Let's do a control. So it lists the stadium. It gives some image information, some other unnecessary stuff, the capacity, and then it gives a row there on line 10, games, and it tells you Russia versus Saudi Arabia, semicolon, separated list of games with the games and the dates. And then it goes to the next stadium, and it lists all the games and the dates and the capacity. So that's the given data, right? And we're going to go to our next query, which shows the requested output. So this, I didn't produce this. This came with the challenge. So this is a table that shows what you want to get out of it, and it shows you the date, the stadium, city, capacity, and the game. So that's the challenge. So how do we do it? Well, here's my solution, and that's pretty much, I think the columns are a little bit different order, but it's the exact solution. It's got 64 rows in it because there are 64 games. And if we take a look at we do it in one query, and let's take a look at the query definition here, kind of get an overall view of it. So you might chuckle when you look at that. So there's no grouping, there's no computed columns, nothing up at the beginning. We're just looking at that initial table with that one column in it called field under bar 1. That's all they gave us. So we use a set of, FlipDB provides a set of functions, just like SQL. You have your standard aggregate functions, sum, min, max. You have all your basic arithmetic functions, plus, times, divide, and then you have all the string manipulation functions, and then you have everything that you would expect as an APL programmer as well. So there's a simple string search function where we look at we grab the rows that have, we identify rows that have games, and we'll look at that for a second just to get the overall scope. Notice also that we have this little hide column off to the right because many of these things we're not interested in our final result. If you think about it, it's just a program, and instead of having the last line only being our result, we have anything that we haven't specified to hide in our result. So let's trace this because it's kind of interesting to trace it and see how we do it. And as APLers, you'll realize that I'm obviously cheating. You know, I mean, it's just not fair. All right, so where's the tracer here? Tools, trace. Okay. So again, we have no. Let's make that a little bigger. We have no computed columns. We have no where clauses, no where not statements, no grouping. First thing we want to do is we want to identify which rows specify the games. So I'm just doing a string search there, and you can see that I've got a little 1. My result is just a Boolean, and we're flagging the rows where the string games : is, right? That's the game flag. And then I want field 1 where game flag is true. So there's a where function, which basically takes a Boolean on the right and sucks up everything on the left and keeps what you want. So we get just the rows, the 12 rows, there's 12 stadiums, and we get that list of games, right? So that's our result there. That's a simple text string for each column. Then we need to split the games. So there's a function called drop car, which takes the left, just kind of like drop, right? We all know what that's going to do. So we're going to drop off the first 6 characters, which is games, semicolon, get rid of that. And then we're going to split it by semicolon. So we get a nested or a partition column, if you will, for each row with all the games. And then we're going to do a count. So we're going to count the number of games in each stadium. And that's going to be important because we're going to need that later. Then we are going to, we want all of these games to be in a simple column. I have them nested here, so we do an enlist. We take a partitioned column and we want to string it out. Notice that we've kept count, though, of how many are in each stadium, but now I want all 64 of them just spread out there. And the same thing for the, so that's the game and the date. And there should be 64 of those things or something. Yep. Yeah, length 64, right? Now we need to split again because we need to get the games and the dates in 2 different columns. So we're going to split on any of these characters to get that to work out. Now I have my game and my date separate, and now I can extract the game by using the first function on the split game and date temporary column, temporary value, and we can extract the date. And here I clean that up a little bit because it's a text string, and I want to put the year on it, and I want to convert it to a date. So I use a couple of functions to do that. And then, what am I doing here? I'm looking for the capacity for each stadium. That's something that we want in each column as well, in a column. And here, I find the capacity, I get the capacity per stadium, and then I kept track of how many games per stadium there were so I can replicate and expand it so that it lines up. So we're using that game count, and we're using replicate, and you can imagine what that does, to get our capacity column. And finally, here to get the stadium and the city, I use a little regex because it was a little messier, and we get the stadium and the city. The same thing here, we have to replicate the stadium and we have to replicate the city to line up with all 64 games, because there's multiple games per stadium. And then we're done. That's it. So it's a pure, well, if you think about it, it's just a pure APL solution, but in the context of a relational database. And you get all the power, everything that you can think of you can do in APL, you can do here with a limited set of data structures. So you don't have, you're not worried about all of the things you can do in APL, but you have basically a column, and a column can be simple or it can be partitioned, and that's about it. So that solution is, I think, fairly unique for a kind of standard database language. All right. Let's look at another quick one here. Let's look at this one. Challenge number 3. So this challenge was to compute running averages, or moving averages, 3 and 6 month moving averages within groups. So if you have, there was a column on the left here, I don't know what any of this data is, but there was this column called HP category, and that changes. There's different groups, 10 HP, I guess that's horsepower for something. And the idea was to produce, let's see, these moving averages here. Oh, actually, this is the input, and there were 6 different things to compute moving averages on, but I think we just did one. Here's the desired output, which is the same with these additional columns to show moving averages. And we'll take a look at our solution here. And I just computed the moving average for the 6 month and the 3 month for one of them. This uses, we make use of operators as well as functions right in the database query language, and they provide a lot of power. I mean, as much power in APL, so we're just leveraging all that power of operators. And we'll take a look at the, at the solution here. Whoops, let's go to the view, query definition. That's the solution there. This uses a couple of unique features. So the idea was to compute moving 3 month and 6 month running averages within this group on this HP category column. And in the first line, everything again here is done in the columns property, or just basically the select clause of the query. And in the first, so we just want some general output there, the HP category, the year and the month. And then the value is text, so we convert it to numeric. So we want to compute a moving average on this field U.S.A, but within a group. So obviously, as you're running your moving average and you go into a next group, you need to stop and start over again. So there's a group function in FlipDB, and this is equivalent to more or less, for those K aficionados, monadic equals. And it basically just produces the indices of all of the different unique values in a column. So we do that, and we note that, called cat group, and notice that we're not going to produce that in our output. So the hide column is 1. We're not interested in it. And then down 2 lines below that, we are using that, and we're applying the average function, which is a typical plain vanilla aggregate function, just like min or max is an average function. But we need to apply it using 2 operators. We're going to first use the running operator, because we want to do a running average. And secondly, we want to do it by group. So we're using the by operator. So those are 2 operators. So the whole thing combines to exactly the function we need, average running by 3 month running average, which is the left argument, and we get our 3 month running average. And then we do the same thing for the 6 month. And that's it. So using operators here really gives you a lot of power. Now in SQL, for those of you familiar, it's kind of complicated. The clauses and they've added this stuff later on, these grouping clauses, and it's I can't figure it out. So it's hard to do. But here you can see it, and furthermore, you can trace this stuff. So you can see what's going on, right? Which again, I think is impossible with SQL. I don't think it's possible to trace SQL in any sense. They have tracers, but they are tracing the execution plan of your SQL, right? Here, you are the execution plan. There's no optimization going on behind the scenes. You, the programmer, you, the writer of this, are designing your execution plan. Maybe that seems a little primitive, but I think it has its advantages. We'll trace this real quickly just to see what happens here. Where's my tracer tools? Trace. Start out, we just want that category column. the year and the month just for identification purposes. Compute, turn that column to a numeric column. Here's the interesting one, group. So the group function takes that column HP category and gives you the indices of where they are, right? So you can see there's 19 different groups. There are even size groups. They're all 72 items in each group. By the way, writing this tracer, I have a little more sympathy when something in the Dyalog tracer does not work exactly as it does when you run the function. I feel the pain. Because this is doing the same thing. That's just an output there. And there's the magic expression. It just does all that. And so on. Boom, boom. All right. Okay, I have, let's see, I have two more of these examples, and I may skip one or two and go on to something more interesting, but let's take a look. All right, what's this one? Challenge 112. I won't spend time on this, but this is another one of these horrendous, dysfunctional sets of data that come up all the time in business. And this was another one of these challenges, but basically it's a questionnaire, and they put each person's answers in a column going out, okay? And there's like 20 or 30 people questioned, and then each row is a question and an answer, and it's idiotic, right? But this comes up, and the desired output is this simple thing where you have one row per person. So we're kind of doing a little pivot. You know, all the stuff was given in columns, you need it in rows, but it's worse than that, right? The way the data is laid out, and you want the information that they've answered there going across in columns, right? So it's a little questionnaire. And this is interesting because normally when you think of doing a query on a table, you're producing something that is in more or less the dimensions of what you're starting with, or aggregating it somehow. But these problems, you're coming up with things that are just completely different dimensions of what you start with, and you saw that with the World Cup games, right? So this is a similar issue, and a quick look at the solution here. This one, I just used a little brute force to do this. And we do something that's even more, let's see here, I'm bringing it over. Here I use an interesting function, the getTable function. This actually returns the entire table that I'm in, because I want to be able to refer to all of the columns in this table, but not by name, whatever they happen to be. So I can, inside the query, I can actually get any table anywhere in the server on any database. And I can now, so T is a table object. And then I extract the values of T, and I get an array of columns. But I don't have column names. So CV is an array of columns. And then I'm grabbing the first 26 because I happen to know, I didn't want to bother with it, but I happen to know that they provided like 200 columns, only the first 26 of which were populated, and the rest were empty in this sample database. So I only have 26 people who were queried, who filled out the form. And then I'm enclosing that into the enclose function. When it takes multiple columns that are simple, it produces a single column that's partitioned, and then we transpose it, and now I can get the stuff that I want out of it. I can pick out the second item, the fifth item, and the eighth item to get those columns that we need in our result. And then the rest is just kind of brute force, fooling around with that data to get the stuff that I want to get. And you guys can all guess what those functions do. Right? There's an each operator. Right? Okay. And that gets that result. And let's see, we have another one here. All right, one more of those, and then we have a final, let's see here. Actually, I think I'll skip this one. If we have time, we'll come back to it. So all of these queries involve functions. The typical FlipDB function is either an aggregate function, a scalar function, or what I call a hybrid function. A hybrid function would be something like sum scan, right, or sort, or grade up or grade down. Anytime you have results that are not row independent, right, but they have the same shape as your whole table. And then there are operators, we can combine them, and we have the full panoply of APL functions that you would expect in an array language. Aggregate functions are built in, so you have things like sum, you don't have to write plus, you don't need an operator to do them. Which is interesting because then the sum function can be used with an operator, or the average function can be used with an operator. So you take a little level out of that complexity by providing functions that have that in APL you would use built-in operators. So there's another class of function that we have, and this is where we're adding a lot of value to the specific business. So a typical function that we might have involves mortgage cash flows. So a cash flow function has many inputs. I don't like functions that have more than one input on the left and maybe an optional one on the right. And virtually every function in there has one item on the right and one on the left. Maybe something like weighted average will have two, a value and a weight. So when you get into business, it gets messy, right? So we have a cash flow function requires up to 50 inputs, and it will have multiple outputs, and they're all different dimensions of things. So an output might be an aggregate cash flow table. You might have the detailed cash flow table. You might have prices and yields. So if you're pricing 100 mortgages, the output will be 100 prices, 100 yields, but it could be thousands of rows of detailed cash flow. And the inputs are also complicated. You might have scalar inputs for the whole process. You might have an item for each row, but you might have prepayment speeds that vary by time for each row, right? So you might have partitioned or nested data as well. So how do you manage all that? So how do we manage a bazillion inputs in an APL function when you want to have one? And how do you let a user put that together? And how do you do that without writing a specific GUI for it? In other words, how do we do it exactly the way we just did these problems? So let's take a look at that. Oops. Get rid of that. I think I have, let's jump here. Okay. Right, so here we have a loan table, and there's this is just a display of the table. It's a query with no property set, just some loan information, I think on 10,000 loans. And that's fake loan data. So here I have what I'm calling a pricing query. So this is, again, just a FlipDB query. Let's take a look at the properties here. Okay. Everything is done in the columns property. So it's just a list of, again, names and expressions. So we grab a loan number, just for display purposes. And the first thing I do there is, I create a new property space. You can guess what that might be. Okay, that's just a namespace. I mean, all these things are more than just that because they have a fair amount of code around them to implement what we need to do. And then I allow the user to specify. That's a generic property space, but down 5 or 6 lines down, we run this function called mortgage cash flow. Mortgage cash flow is a complex function that takes a single property space as its input, and allows you to specify anywhere from 1 to about 50 different inputs. Here I've only specified a few. And on this line, obviously, you can write an expression, you can write a simple name, you can clean up your data as you're going. So the second line there, I specify the balance. In this case, this is the same name. The requirement for the function is the word balance, and it happens to be the same name in my database. Rate. Service fee, I just want to give it a constant. It could also vary. The term actually needs a different name, so the original term goes to term. And then here, prepayment rate scenario is an input that can be time varying. It doesn't have to be, but it can be. So there's an industry standard called PSA. The generate PSA function is an industry standard. It produces what's called a curve, 360 item curve. And this industry standard, you can give it 100%, 150%. It's a percentage of something. So that function stands on its own, generate PSA, and just produces an industry standard 360 item vector. However, I want to apply that. I can't just assign it in there because I could have 1,000 loans, 1 loan, 200 loans. I don't know how many are there. And if I want that to apply to all of them, it has to conform. So we enclose it. Again, just what you do in APL, right? If I put a single scalar there, it would have a constant prepayment speed for every loan for all time. So that's that. Then I get 2 other inputs. I can give it a stated price and or a stated yield, either one of those. Then we run it. And the result is also a property space, and it has a bunch of things that we can get out of it. So I want to display the computed price, so I just grab that and I round it, the yield. It's fairly complex, so there's some simple stuff in there, and then you'll notice I'm dotting 3 times on that next one, total service fee. Go in there. There's a cash flow name, subname space or some property space, and it has a bunch of all the detailed cash flow. So there I want to sum up the cash flow, and then also I want to take a present value of that cash flow and see what it is. And the last line gets to another feature of this thing that we're looking at, which is an array of queries, not just one. Those arrows up there, we're stepping through queries. So just like a single query can be thought of as a defun, a set of names and expressions, right, producing this table as a result. This report or dashboard or array of queries can be thought of as a more complex dynamic function. So you have this query, and then there's another one that's executed after it, and it can refer to everything that's in the previous query. So if you have a query that produces some interesting numbers, your next query in your series can refer to anything in it by name. And one way you can refer to it by name if you've got it up here directly, but there may be things like this entire output CFO that I want to provide to the next query. So there's a global space that you could put in additional things as well. And so here, the entire output of CFO, I want to be available on my next query. So that is right here under aggregate cash flow. So here's the aggregate cash flow output from that previous query. And I don't have to really do much of anything to display it. This is a huge table of data. It goes on and on and on and on. And it could be, actually this won't be very long because it's aggregate, but that's all I have to do to get it in the next query because it refers to the previous query. In this case, I did it explicitly, but I could refer to any column in that previous query without actually assigning stuff in there. I could just do globals dot, whatever the name of the query was. Pricing. I could refer to pricing dot whatever I wanted to. So that's the aggregate cash flow. And then one more. There's detailed cash flow. So this thing has in it, this is the third query here in a row. And let's change the view to the grid view here. This thing has in it, I don't know, over 300,000 rows, right? All the detail. And, wait a second here, whoops. take a look at that. Globals.cfo.cashflow is a property space. And if you transpose a property space, you get a table. And I want to, this is a nested, all the columns are partitioned because it's a cash flow for each mortgage, but I want to display the whole thing simple, so I enlist each. And the result is kind of unimportant here. If you only give it back one thing and it's a table, you don't need to give it the name of the result immaterial. And so we get the detailed cash flow that way. And you could pick out a particular cash flow and do more work on it or what have you. So, so the goal there was to let people do extremely complex business functions, get the full power of using the FlipDB environment, and which is obviously leveraging APL to the hilt in terms of the design, without doing rich GUIs. We'd never be done with that cash flow thing if I had to do a GUI for it, right? It's a losing battle with some of these things to try and put a GUI on them with all of the fields and everything that you need. So the concept of just having that property space, allowing the user to specify the inputs, to clean up the inputs as you go along if you want to. I mean, often you might want to do that in a separate query first to, make sure your data is good, quality control, and all that sort of stuff. I think I'll leave it there so there's a couple times for questions and a couple minutes for questions. And one last bit about this is that the idea has been to avoid, we provide a scripting environment that you can go to and you can script the whole thing. But the idea is to pretty much avoid scripting at all costs, simply because it's always a leap of effort for the user to script. And with this, we've really taken a huge amount of stuff that would normally have required scripting, because you can have an array of queries, because every query can refer to something within itself, and every query can refer to any previously executed query in this array of queries, which we just call it a dashboard. A dashboard with, as you see, no graphics at all. We're strictly the numbers. We don't have any pictures, we don't have any charts, we don't have any bar charts, none of that. And then be able to put that together into a single thing, and then to be able to take it and look at it in its entirety. So if we look under this, here is the entire, essentially it's a script, but no one really thinks you're writing a script. So this is a 3-item dashboard with 3 different queries, and it gives you the properties of all your queries. So you can follow, okay, these last 2 are almost trivial queries, they don't really do much. But the whole thing is laid out here, and you can see everything, and you can scope it out and see exactly what you want to do, what you've done. And there's nothing hidden. There's no mystery about where something got computed at all. It's right there. So that's I think I'll wrap it up. Thank you.